Hey everybody. So thank you for watching this. I'm glad you want to be prepared for this quiz because, yeah, this is the kind of problem that I actually value much more than like the simpler like flagpole problems because you have to do a lot of thinking in this kind of problem. And if you can do this, I claim that you're going to be a better problem solver just in life. Hey, so digging into this, I know this looks like a really difficult problem because of all the reading, the vocabulary, numbers, and everything, and it's not obvious how to do it. This is a kind of problem that I'm certain that if you can do, it's going to be more useful for you. And I know that your other classes may not have trained you to do this kind of work, but I promise if you keep trying, you're going to look back one day and realize this problem was actually super easy. Okay, I know you're not there yet, but you will, I promise, if you keep plugging at it. So you're going to find as you do more problems of this type, it really all breaks down to the picture. If you can understand the picture that it creates, and that picture really is just one of the mathematical structures that you're very familiar with at this point, and you're able to solve at this point, then this problem poses very, very little issue. Okay? Now, this actually follows a very common trope within the world of physics and mathematics, which is the trajectory kind of problem. You've experienced this in life. I guarantee you have, because I'm sure everyone's taken a ball and tried to throw it at something or somebody, but you missed. And so you had this line where in your head, if I throw this ball, it's going to hit a target, but then it turned out to be off. And so it traveled a completely different line. I can kind of demonstrate that in drawing. I'll draw a messy one now, but I'll go back to the real thing. But if you're standing right here and you're trying to hit your friend that's right there, you can throw a ball or in your mind that goes straight to your friend. Okay? But sometimes, since we're not perfect at throwing, instead of going where you intended to go, it ended up going off to the side or above or below or off to the left or something, right? And so when I say a common trope, this is what I'm talking about. This is a classic trajectory problem. This was the intended course. This was the actual course, which means the distance between the two is the error. Okay, also sometimes referred to as the miss, how much did I miss by, right? Any baseball fans in the video watching right now sees this all the time through the course of the game. You intend to throw it right where the catcher wants to catch it, but sometimes it doesn't go that way, and so the catcher has to adjust because you missed the target. And so you can even see with this very basic example, we are creating very familiar geometric structures. In this case, we're creating triangles because we have a line here, then we have another triangle involved, and then we can start using principles like similarity and scaling to actually find errors and misses. This is why I keep saying this is one of the most important things you can do in math, because it's such a common situation, right? And so if we can just demystify and break down this problem a little bit, I think you're going to be in good shape, all right? Now, the way I usually approach this is I focus completely on the picture. I don't care about numbers. I don't care about solving or what I'm going to have to do for conversions and all that stuff. All I care about right now is I have a good quality picture. Good quality pictures mean good quality proportions, and then you can let your natural algebra ability just kind of take over. Right? And when you look at a problem like this, and you should ignore the numbers for now, just look at the objects. What kind of objects are in this picture? That's what we should draw. Okay? And we should also kind of be conscious of reducing our drawings down to some very simple representations. And so in other words, we shouldn't worry about drawing a hyper-realistic Earth or moon or probe. Break them down to what really matters, which are typically points, lines, maybe planes, because it always represents a location or a distance, which is why we start geometry talking about that kind of stuff. And so I'm not going to read the problem out loud, but you might want to pause and read the problem or read what you have on your paper. Right? And as we start to talk about the objects, hopefully that'll make more sense if you do so. Okay? So one of the objects here is Earth. Right? So Earth, I'm going to reduce down to a single point. I will label it E for Earth, of course. So this Earth now is going to be the starting point of this probe. Okay? Now it does have a target, which is Mars, so I'm going to put it way the heck over here. And so the problem proposes that the NASA engineers are trying to make the probe land on Mars, or at least a target zone on Mars, right? And so ideally, they pointed it at something at the planet, they shot it off from the ISS, and it's going to travel in one direct line, essentially, right to its target, okay? Now, of course, that's oversimplifying it, but those of you guys have more astronomical knowledge. I'm not trying to dive into details, but that's what is going on. And so we can think of this line as the intended 10, ooh, man. There we go. The intended trajectory. Okay, and trajectory just means pathway, right? So that's what was meant to happen in this for like what the satellite did. However, that's not what actually happened. And so like what actually happened is when they launched this probe from the International Space Station, which is essentially right on where Earth is, instead of going right where it should have been, it was off a little bit. Okay, I don't know which direction it was off. It doesn't really matter because we just have to represent this thing as being like off target or off course. And so like at some point it passes the moon, and they notice that the distance between the moon and the probe of where it is off a little bit, which means we have another location we should track, and that's going to be the moon. Now this is of course not representative of how far those things really are, but we're just trying to get a picture of what it looks like. Okay, and so once it passes the moon, okay, the distance that it's off is going to be 300 feet. Okay, and we'll worry about unit conversion later. Okay, and so the NASA engineers have to have this like thought. Either we correct it, which means like we would do something like this, where we bring it back and re-aim it at the moon, which could be costly and expensive because they have to send a bunch of signals to this moving object. Or we just ignore the fact that it's off, and we hope that even though it's going to continue kind of on this wrong path, by the time it gets like where Mars actually is, how much is actually off is not that bad. So like the amount that it's off, like the amount that it misses, is still within acceptable range, and the acceptable range in this problem is 5 miles. And so even though we don't know this distance, which I'm just going to call an x, I do know that x has to be less than or equal to 5 for it to not have to be corrected. And so that gives us a target for our answer, but we still going to have to calculate the x value. Okay? Now to finish this out, hopefully we're taking a step back and realizing that we just have a couple similar triangles, the small one stacked on top of the longer large one. We're going to need some distances, and they do provide those distances, right? So at this moment they notice the error. The probe was already 238,900 miles from Earth and had another 33,361,100 miles to go. Hey, so where to put these numbers? Well, they knew how far it had to go to get to the moon, and so I would actually claim this distance was the 238,900 miles. Okay, and then this entire pink distance, this partial pink distance from like here to here is going to be the 33,661,100 miles to go. Okay, because that's going to be the additional distance it has to make. Okay, I think there could be an argument that it goes along the blue line, but I'm going to go ahead and put it here because I think in terms of calculation, it's not going to matter too much. Okay, and so like this is very like messy because I've written some stuff on it. But if I try to now simplify this picture, well, let me adjust that. Oh, there we go. Okay, so if I do a little cleanup here, okay, I essentially have a very, very familiar picture. The numbers aren't super nice, but they are serviceable. And so I have this stretch, which is 238,900. I have this stretch, which is 33,661,100. I have this bit, which is 300 feet. And then I have my target that I'm trying to find, which I'm going to call x. Okay, and so again, we have similar figures. We have the reflexive angle here. We can assume that the direct path would be at perpendiculars to the mist because that's how we measure distances away. And so we can proceed in setting up a proportion and solving. So I'm going to take the x first because we always should start with the thing we don't know. And I'm going to compare it to, in this case, 300. Okay, so I'm establishing a ratio of corresponding parts, large to small. So we should do the same thing for the top and bottom of my matching ratio. If they're similar, they're proportional. If they're proportional, it means we have two ratios the same. And so my first ratio, x300, is a large triangle over small triangle, corresponding parts. And so should my next one. Now, I do have to be careful because I have to add the entire distance. And so I have to start with 33,661,100, add the 238,900 miles. And that will give me a top value of something crazy here. 33,900,000 miles. And that's going to be over my short distance, 238,900. Okay. So now proceeding and solving, we'll multiply by 300, and then we'll divide by 238,900. Okay, and that will give me an x value of 42570.113. Okay, now we do, so knowing that we can't miss by more than 5, which is something we established up here, you could look at this number and say, oh crap, well that's way more than 5, it's going to miss by a bunch. But we should note that this value is actually in feet. Okay, now I know some of you guys are going to want to convert this to miles right off the bat. But that's not necessary. We just have to understand our answer is in feet, and then we can just convert our answer to miles for an analysis. And so knowing that there are 5,280 feet, oh, that was super messy. Okay, so knowing that there are 5,280 feet for every 1 mile, okay, and I currently have 42,570.113 feet, I just have to solve for number of miles. The eagle-eyed amongst you might notice this is a proportion too, and that's because our scaling factor is actually a ratio, and we have to make the ratio on the right work. Lo and behold, we got another proportion to solve. So again, we're going to cross multiply. Okay, so 42570.113, divide that by 5,280. Okay. Which means that our miss, in other words, our x value, is going to be 8.063 miles. Okay, so we had this problem set up, okay, knowing that our miss, the amount that we were going to be off from our target landing zone, could not be anything more than 5 miles. 5 miles was our maximum miss. Okay, otherwise the probe would be in the wrong part of the planet. It's going to be very bad for everybody. And so we set up our similar triangles. We solve using proportionality the way we know how. And we end up with the miss being just over 8 miles. And so the question is, should the NASA engineers make an adjustment? Should they worry? Yeah, they should worry because they're going to miss their target zone by just over 3 miles. And although I guess it's a possibility that it'll still hit, it's very, very small because of the distance that you can expect it to be off. Okay? And so that's how you handle this kind of problem. It's, like I said, it's even though it looks complicated, it's no different than even like a pole shadow problem, right? You have to draw all the elements. You have to find the similar triangles because that's what we're studying, of course. You have to find the values because the values are important. Okay, set the right proportion, solve for the value, make sure you're solving for the problem because the value is not always a problem. In this case, it took some conversion. If you were to convert 300 feet right off the bat to miles, it looks like it's going to be 0.05681, 82, rounding here is very important. And so if you don't follow proper rounding rules and you write it as like 0.06 or 0.1 because you're improperly rounding not to 3 digits, your answer is going to be very different. This is why the NASA standard is 3 digits, because it maintains high accuracy. And so make sure you're doing the same, right? So that's a recap. Remember, if you have any questions, you still have a couple, at least a day before your quiz, depending on when you watch this. So come see me before, after school, Spartan time, something along those lines. And any problems that you're having, we'll sort out. Right? Thank you guys for watching.